Friends, you may recall that to send data through a transmission media, you have to convert it into a signal. The signal can be electromagnetic or optical signal. Now, the today's talk concerns with data encoding techniques. What is data encoding technique? Data encoding technique is the process of mapping data onto signals. So, it is process of mapping data to signal. We know that data is available in two forms: digital and analog. The signal also can be of two forms, digital or analog. So, these two together leads us to four possible combinations. These possible combinations are digital to digital, analog to digital, that means digital data and signal is also digital. Analog's data and signal is digital. Other alternatives are, you have got digital data and then your signal can be analog, or your data can be analog and signal can also be analog. For example, when you are converting digital data, you will use a suitable device, say a transmitter. Which will convert digital data into a signal, digital signal. Example of conversion from analog data to digital signal is codec. Codec stands for coder decoder. And from digital data to analog signal, you can use a device called modem. Modem will convert digital data into analog signal, which can be sent through a analog line, telephone line, for example. Similarly, analog to analog conversion can be done. A typical example is a telephone line. In a telephone system, your that signal data is also analog, signal is also analog. Now, you may be asking, why encoding? Why it is necessary to do encoding? First of all, let us try to understand what is our objective. Our objective is to transmit, send data, or transmit or send data, or send signal through a medium. Now, given a bandwidth of the transmission media, Our objective is to send data at its highest data rate and with minimum error. So, objective is high data rate and low error. We know that an increase in data rate increases error rate. We also know that an increase in signal to noise ratio decreases error rate. We also know that an increase in bandwidth increases data rate. Now, these three we cannot really change in the sense if we want to have higher data rate, your error rate will increase. So, our objective will be to transfer that data without increase in data rate by suitable encoding technique. And also would like to have low error rate for a given signal to noise ratio. Similarly, an increase in bandwidth increases data rate. That means the bandwidth, higher the data rate, but higher is the cost. So we have to optimize the use of transmission media. How? We shall use suitable encoding technique so that we can optimize the use of transmission media in terms of data rate, in terms of error rate. Now, before we discuss various encoding techniques, let us consider the parameters involved in this connection. In other words, how do we characterize a particular encoding scheme, whether it is good or bad? To do that, we must have some parameters with the help of which we can characterize that, okay, this is good, the other one is bad, or this particular property is good for this encoding scheme, this particular property is bad for the other scheme, and so on. So let us see what are the various properties or parameters involved in this context. First of all, signal spectrum. Your data has some signal spectrum. We have already discussed for different types of data, voice, video, and so on. What are the different spectrums possible? Now, after doing the encoding, the spectrum will change. Now, we have to modify the spectrum of the encoded signal in such a way that it can be transmitted through the medium with less attenuation and less distortion. In other words, we have to match the spectrum with the bandwidth of the transmission medium. So that's why the signal spectrum plays a very important role. Second parameter is clocking. As we shall see, your signal will have some duration, bit rate, and so on. So it is based on some clock. A clock will be necessary to generate the signal for a given data. Now at the receiving end, it is necessary that the clock frequency of the receiver is same as the clock frequency of the transmitter. How that can be done? One possibility is to send the clock through a pair of wire. So you will require a separate pair of wire to transmit clock from the sender transmitter to the receiver. But that is not feasible because that will require an additional pair of wire, which is very expensive. So the alternative is to regenerate clock from the signal received at the receiver. To do that, what you have to do, you have to use some special hardware such as phase lock loop, which will regenerate the clock, and that can be used at the receiving end, and that clock frequency will be same as the transmitter clock. However, the encoding has to be done in such a way that the clock can be regenerated in a efficient manner, regenerated with ease in the receiving end. So the clocking plays an important role in the encoding technique. Third is error detection. We have seen that while passing through the transmission media, the signal will be suffering from distortion, and noise will be introduced into it. So in presence of noise, in presence of distortion, you have to detect the signal at the receiving end, and you have to detect when there is an error. So error detection is also important, and we have to find out which particular encoding technique helps you to detect error efficiently. Then signal interference. And noise immunity. Encoding scheme should be devised, should be used such that the signal interference, external interference, and is less. It is immune to various noises. So that is another property which we have to look into. Finally, any encoding technique will involve some cost to implement that particular scheme. So cost of implementation and complexity. So complexity and cost of implementation will also play an important role. If the encoding scheme is very complex, requiring very high cost of implementation, that may not be used in many low cost equipment. So cost and complexity will also play an important role. So these are the parameters we have to see to evaluate various encoding schemes that we shall discuss. So our overall scheme will look like this for digital data to digital signal. First of all, we shall consider digital data and digital signal of the four possibilities that we have discussed, because this is one of the most common that we shall encounter in our data communication that we use in computer networks. So we have digital data that is, let it be represented by GT, and we shall be using a device, say encoder, and that encoder output can be represented by XT, which is digital in this case, because your signal is digital. So here you have your data and you are generating the signal XT by the help of an encoder. Then at the receiving end we will require a decoder which will convert the signal XT back to the data GT, which is digital data. So this is our conversion process. GT is converted, it is a function of time. We have seen that the data and signal are functions of time, and it is converted into digital data and digital signal, and again it is converted into digital data in the receiving end. So here in the at the transmitter end TX, and here it is in the receiving end. These two processes will take place. Now, in this context, let us define some parameters that is used for signal. Say in the simplest case, your data can be represented by sequence of zeros and ones, say 0 0, say 0 1, 0 1, 1 0 0. This is your data. Simplest possible representation in the form of signal, we can be, say it is low for 0, low level signal, and high for 1. In terms of voltage, it can be 0 volt and it can be, say, plus 5 volt. So this is low, again 0 volt, and high for 1, and again low for 0. So we see here this data is being mapped to signal, and this is the representation of the signal in terms of voltages. Here you see this particular time is known as the bit duration. This period is known as bit duration. That means duration of a digital bit, digital data, or rather digital signal. That is the bit duration. And correspondingly, you can have data rate, which is rate at which data is transmitted. And it is expressed in bits per second, or BPS. That is a unit for data rate. Let us now consider various encoding schemes or encoding formats. Broadly, the encoding scheme can be of two types. First of all, uh, you can have two possibilities: two level multi-level. You can have two level because it is binary. It is also possible to represent using multiple levels. We shall see later how the signal can be represented using three levels. And again, in two levels, there are two possibilities. One is known as NRZ, non-return to zero. That means during a bit duration, if the signal returns to zero level, we call it, and does not return to zero level, we call it not return to zero, NRZ. Another possibility is RZ, return to zero. That means for each case during a bit position, the signal will return to zero during a bit duration, RZ. That corresponds to return to. So in these, there are some other varieties. For example, it can be unipolar. The signal can be unipolar in the sense it can have only one voltage level. That means either positive or negative. Or it can be bipolar, where two voltage levels will be used. That means it can have both positive and negative voltage levels. So these are the various possibilities. Let us consider some of the popular encoding schemes. Say this is our data. Data is say 0, 1, 0, 0, 1, 1, 0, 0, 0 and 1. And your signal, the simplest one, as I said, can be represented by 0 with a low level, 1 with a high level, 0 with low level, 1 with high level, 0 with low level, and 1 with high level. This is one of the possible schemes. And one commonly used scheme, which is very similar to this, is known as NRZ L. NRZ L stands for non-return to zero. L stands for level. In this case, 0 is given a higher level, high, and 1 is given a low level. it is just the opposite polarity of the previous one. So this is the NZ L. Let us see what are the properties of this NZ L technique or NZ L scheme. First of all, it is simple and it has direct correspondence with the data, and rather it can be very easily mapped from data. The signal can be very easily mapped 0, 1, wherever there is a 0 you get 1, wherever there is a 1 low level and so on. So using low and high levels it can be very easily implemented. So it is simple and easy to implement. And let us look at the spectrum. If you remember, we discussed about the important properties, signal spectrum. What about the signal spectrum of this particular signal? The signal spectrum of this will be in this range. So this is the signal spectrum for NZ L. You see here the signal spectrum lies in the range of 0 to energy lies between DC, it has got a DC component, 0 frequency, DC component. Here the scale is normalized frequency in the x direction and mean square voltage per unit bandwidth in the y direction. So that gives you the spectral density, and here you see the main concentration of energy is from DC to half the bandwidth, DC and half data rate. What about clocking? In this scheme, you see here, whenever you have got long sequences of ones or long sequences of zeros, there is no transition, and as a consequence, in the receiving end, it will be very difficult to regenerate the clock. So synchronization is difficult. We can say that synchronization, sync fails for long sequences of zeros and ones. Whenever there is a long sequence of zeros and ones, there is no transition, and at the receiving end clock cannot be regenerated. However, the bandwidth is very small, which makes it very attractive, and this is one of the disadvantage. Synchronization failure. Let us consider the second scheme, which is known as NZ-I. NZ-I. In this case, whenever there is 1, whenever there is 0, there is no signal, and in case of 1, the signal is inverted. That's why it is called The name is non-return to zero invert on ones, or in short NRZ-I. In this case, for 0 there is no signal, and in case of 1 there is an inversion. So the signal changes from this level to low level to high level. There is a signal here, and it remains until it encounters another one. So here there is another one, so it changes from high to low, and again it changes from high to low here, and it continues until again here it changes from high to low. So here the number of transitions, as you can see, is much less, and of course for alternate sequences of zeros and ones it will be same as NRZ-L. So spectral density will be same as the NRZ-L. So you can say that spectrum will be same as NRZ-L. So NRZ-L and NRZ-I have the same spectrum. What about the other properties? First of all, it is differential encoding. What do you mean by differential encoding? In case of NRZ-L, if you are sending signal using a pair of wire, if this pair of wire changes, gets replaced by one gets replaced by the other, what will happen? The polarity of the signal will change, and it will at the receiving end the 1 will be detected as 0 and 0 will be detected as 1. So when you are sending through a long distance, in many situations this change will occur. It is very difficult to keep track where these pairs of wire are getting positive, getting negative, negative getting positive. But if it is a differential signal where the change is by transition, not by levels, then it is independent of the polarity. That means it is polarity independent. This is very attractive, and secondly, it is also easy to implement. And so far as the energy is concerned, most of the energy lies in the range of DC to half data rate, same as the NRZ-L that you have already seen. In both the cases, one important limitation is there is a DC component. So in this particular case, in case of NRZ-I, we find that there is a DC component. Present, which is disadvantageous because most of the communication channels or transmission media cannot transmit DC. We shall see that the bandwidth of the channel cannot pass DC. So DC component is a disadvantage. Lastly, another disadvantage is lack of synchronization capability. Just like the previous case, Energy L. Here also, when you have long sequence of ones and long sequence of zeros, there is no transition, and as a consequence, in the receiving end, clock cannot be regenerated. Synchronization will fail. So, this is a disadvantage of energy I. Let us now consider another scheme which is known as Manchester. This Manchester encoding, it is also known as biphase. As we shall see, for each and every bit there will be two parts. For half of the bit rate, bit duration, there will be one level. For remaining half, there will be another duration. And in Manchester encoding, for one, there is a transition from low to high in the middle, and for 0 there is a transition from high to low. So on this diagram it will look like this. For this one there will be a transition from as I said, from low to high. So it will be low to high, and for 0 there will be transition from high to low. That means here for there is another 0. So here also there will be transition here, and signal will be like this, and for 1 there will be transition from low to high, and for next one again it will be from low to high, so it must change here, and for this low again low to high, for this 0 low to high, this 0 low to high, so it will be like this, and for this one it will be from high to low. So this is the signal that we get using Manchester encoding. And here we see there are lots of transitions, and even for each and every bit at least there is one transition, and for some of the bits we find there are two transitions. Here we find there are two transitions, here there are two transitions, here there are two transitions, and so on. So if there is a continuous sequence of zeros or ones, then there are two transitions, and if there are alternate ones and zeros, there is only one transition. What is the implication of this? Implication of this is, at least as I said, one transition per bit duration, and because of that it is self synchronizing. By self synchronizing we mean the number of transition is so high at the receiving end, the signal can be very easily regenerated, the clock can be very easily regenerated. That is why it is called self synchronizing. What about the spectral density? Let us look at it. For Manchester encoding, the spectral density will be like this. Here we see the signal spectrum is much wider than the previous two schemes. So This is for Manchester. And we can write that the high bandwidth and signal energy lies between half data rate to 1 data rate. That means uh, from this region to about this region, you can say about 1 data rate the signal spectrum is lying. So 1.5, 1 data rate to 1.5 data rate. So it requires more bandwidth. Now what about the clocking? As we have already said, self synchronization, and it also facilitates error detection. It facilitates error detection because of the number of transitions that is occurring and the coding that is used. You can detect the transitions for each of the bits more easily than you can detect the levels. There is another variation of this which is known as differential Manchester. In case of differential Manchester, uh, differential Manchester for 0 there is transition in the beginning, and for 1 no transition in the however there is always transition in the middle. So there is no transition in case of 1 in the beginning of the bit, but there is always transition in the middle of the bit, both for 0 as well as for 1. So it will look like this. Say for this particular case, since this is a 1, there is no transition in the beginning, but there is a transition in the, let's assume the transition is taking place here, and for this 0 there will be transition in the beginning, so it will go here, and then there will be transition here, and this is another 0, so there will be transition in the beginning and another transition here, and this is 1, so there will be no transition, but there will be transition in the middle, and no transition in the beginning of the next one, but there is transition in the middle, and this is a 0, so there will be transition in the beginning and also in the middle. For next 0 again transition in the beginning and in the middle, in the beginning and then the middle, and for the next one there will be no transition here, and for the 1 the transition is in the middle. So this is how the signal that we get for using differential Manchester encoding. This differential Manchester encoding, so far as the spectrum is concerned, the signal spectrum is same, Manchester or differential It is the same. It does not change. Now, one very important point that you should notice here, in both the cases, the bandwidth is more. And so, for the same data rate, what is the signal rate or signaling rate? For Manchester encoding, we find that signaling rate is double that of the data rate, and that's why it is called baud rate. And this baud rate is expressed by D is equal to data rate by B, where B is the number of bits per signal element. So we see that by different encoding, the baud rate may be increased. And for Manchester encoding, as it requires higher bandwidth, the baud rate is more. And that is the reason why, although it is preferred in local area network applications because of self-synchronization capability, because of higher error detection capability, but it consumes the bandwidth. So for long distance communications, it is not preferred. In my next lecture, we shall discuss other encoding scheme where we can conserve the bandwidth, and we shall see how we can make the encoding scheme suitable for long distance communication using suitable encoding technique. Thank you.